Audible? Okay. Good morning, everyone. I'm Anjali Dhabu. I am doing my postdoc at University of Hamburg with Celine here. And I'm going to present some work that I did in my PhD under the guidance of Dr. Raghukant. So today I will be talking about the simulation of translational and rotational ground motions. We know that the characteristics of the ground motions are affected by three main factors. First is the seismic source. The second is medium of wave propagation. And third is the boundary conditions. So in my PhD, I have tried to address the modeling aspects of all these three factors. We start with the earthquake source. So seismic sources are generally represented as rectangular regions where the slip is distributed all over the surface of the fault plane. You can see that it is having the length and depth and the intensity of slip on all the subfaults. Whenever we see a fault model like this, there are regions which are actually responsible for the peak amplitudes that we observe on Earth. These regions are defined as regions of asperities. You can see it here. The whole slip model is generally characterized using standard statistical distributions like normal distribution, exponential distribution, log normal distribution, etc. But we know that all these distributions do not actually cater for the large or for the highest values in the data set, be it any data. So this applies for the slip model also. So the question arises that can we use some other statistical approach to model these regions of asperities or the regions of strong motion generation? If we have to do the statistical analysis, the first thing that comes is we should remove zeros from the data, or rather finding the effective dimensions of the slip from a raw slip data. The top figure shows a raw slip model. In this work, I have defined the effective slip such that each and every subfault should contribute to 90% of the total cumulative energy that is observed. The figure that is below, you can see that a large part of the yellow part has been removed in the effective slip sample, and the yellow region is nothing but many zeros in the raw slip model. Once I have the effective dimensions or the effective slips, I move to determining the regions of strong motion generation. If we see the quantile plots, it's a standard quantile plot for exponential distribution. You can see that initially for the slip model, it nicely follows an exponential distribution, but the highest values of data set are deviating. I follow the method that was proposed by Cirillo in 2013, and I determined that how can we get these regions of strong motion generation. The blue dots here show the standard effective slip, and the black dots are showing the regions of strong motion generation, which are nicely following the Pareto distribution, or they fall in the Paretian zone. This shows that this can be a better method to represent the regions of asperities or regions of strong motion generation. Finally, for a given 1991 Sierra Madre earthquake, you can see that the dark black lines are actually showing the regions of strong motion generation, and they are actually able to capture the highest, the subfaults with the maximum slip values. So once the methodology was developed, I have applied this method on 159 rupture models to determine the effective length, width, area, mean effective slip, the threshold slip. The threshold slip is the number that will define that, okay, above this particular data, the slip will follow a Pareto distribution. And then finally, the area of strong motion generation. These equations can be used to predict the rupture parameters for any given future earthquake. Once we model the earthquake slip properly, the next parameter that comes is the medium of wave propagation. Classically, we all assume that the Earth medium should be modeled as a classical elastic half space. However, there have been theories which talk about that the seismic wave propagation in granular medium should be dealt with using reduced micropolar theory. Reduced micropolar theory comes from actually micropolar theory, which was proposed by Cosseret brothers in 1800s, and it was picked up by Ehringen in 1956 and thereafter by Nowacki in somewhere around 70s. These are the equations of motion for a reduced micropolar half space. You can see that there are two equations. You see a rotation component also that is represented by theta here, and u is the displacement. C1 and C2 are the wave velocities. You see that there are two additional material parameters in the equations. One is kappa and the other is J. J represents the rotational inertia of the medium, and kappa represents the stress between the two, or intergranular stress. When we compare these equations with those of the classical elastic half space, we can see that in the classical elastic medium, rotation does not come in the standard equation of motion, and these are the C1 and C2 are the wave velocities. So once we have this, if we see these equations of motion, it was interesting to see that how we get the translations and rotations using this theory. So for a homogeneous half space, I considered that there is a source that is acting at a depth of S, let us say, and the plane of loading divides the whole half space into two regions, region 1 and region 2. In region 1, obviously, there will be a transmitted wave and the reflected wave, and region 2, there will not be any reflection. When we do the dispersion analysis, we see that there is a drastic band gap that is observed in the shear waves. This characteristic we do not observe in classical elastic medium. Okay, so I did the whole of analytical formulation, and I obtained the displacements and rotations. I will just show here two important results that we got. For a homogeneous medium, the left panel shows the translational velocities and the right panel shows rotational velocities. You can see only one line in all the three graphs on the left panel. However, there is a difference that is observed in the lines on the right side. On the right side, I have done a small parametric study to see that how these additional parameters affect these ground motions. It is evident that the translational velocities are not affected at all by the two additional material parameters kappa and J. However, there is certainly a difference in the rotational velocities. As we change the intergranular stress, the rotations that are observed on the Earth's surface, they are changing. However, this study was done for a homogeneous half space, and we know that it is not a very realistic way to model the Earth medium. So the next step was to model it as a layered reduced micropolar half space and to see that how the rotations look like. So again, in a standard way that a layered medium should be dealt with, I divided the problem into PSV and SH wave propagation and obtained the results for translations and rotations. Once I did that, it was first very important to validate the method, whether the analytical formulation that has been done is correct or not. So I validated it with classical elastic medium. So in reduced micropolar theory, for a certain combination of extra material parameters, the theory comes down to the classical elastic medium. So for that, for both those conditions, I validated the methodology first, and we saw that the response for the reduced micropolar half space matches exactly with that of classical elastic medium. So we were sure that, okay, whatever analytical formulation is done was correct, kind of. Then I moved to simulating the ground motions for an actual earthquake, which was a 6 magnitude earthquake that occurred in 2012 in Wutai, Taiwan. And it occurred at a focal depth of 26.3 kilometers and was recorded at a radial distance of 161 kilometers. This is the medium that has been studied, that has been given for the Taiwan region. It's an 8-layered medium. The standard material properties, that is P wave velocity, shear wave velocity, and density, have been considered from the literature. However, the two additional parameters, that are kappa and J, we still do not have these material properties experimentally. So I have considered these material properties by trial and error. The only thing that I have taken in mind is, if we see the topmost layer of Earth, the medium is more granular, and as we go down, obviously the size of grains is going to increase, so the rotational moment of inertia will correspondingly increase. And same will happen with the intergranular stress as well. Now, if we see the translations and rotations, this is what we get. This is the comparison between the translational and rotational velocities for a reduced micropolar half space and for a classical elastic medium. The red line shows the reduced micropolar medium and the blue line shows classical elastic medium. As we observed for homogeneous half space, there is no difference in translational velocities here as well. However, when we see the rotational rate, there is a drastic difference. And also, the rotational velocities that we obtained about the vertical axis, the peak value matched with what was reported in the literature. So this gives us an idea that maybe this theory can be explored further particularly for simulating the rotational ground motions. Once we are done with the source and the medium, we moved to the topographic conditions. If we see the Indian subcontinent, the northern region of the Indian subcontinent consists of Himalayas, and it has a very complex topography. People have already studied the amplifications in ground motions due to ridges and valleys when they are subjected to PSV or SH waves. Some type of numerical work has also been done for other regions of the world, where they have modeled everything numerically, considering the topographic variations. However, this type of study was not done for the Himalayan region. So we picked up this region. Now, in order to simulate ground motions here, analytical approach cannot be of much help. Therefore, a 3D finite element model was developed for the central seismic gap of Himalayas. The figure in between shows the finite element model. And you can see that it is not just the Himalayas that consist that region, but also a huge part of the Indo-Ganga basin exists there, which are alluvial deposits because of the river. And there is a drastic change in the material properties that is observed. So that was also considered in developing this model. So the variation of material properties with respect to depth has also been considered. Once the model was developed, it was validated for 2 past earthquakes. And then we calculated the amplifications for a hypothetical earthquake of 8.5 magnitude. The amplifications were defined as P ground displacement or velocity at the topographic level to the PGD or PGV at the same station when topography is not considered. And these are the types of amplifications that we obtained for displacement and velocity. And regression analysis was also carried out where the equations can be used for some type of future earthquake. So finally, after doing all this analysis, we saw that, okay, are quakes common just on Earth? Of course not. From the last few sessions, we know that we have seen activities on Mars and Moon both. So in the absence of recorded data, how do we know that there was a quake that happened? On Earth, it is very easy because people observe it, people feel it, we see buildings falling, getting damaged, etc. But on these planetary bodies, they are the boulders which tell us that, okay, there was some shaking that occurred. And these boulder falls are observed on the satellite images. The standard way to characterize that how much PGA must have occurred is equal to the B/H ratio of the body. But that gives a very crude estimate of the PGA and also the radial distance up to which that shaking must have been observed. So better way is to do some dynamic analysis where we have the simulations and we subject those simulations to these equations and we see that whether the boulder toppled. So on Moon, we simulated some ground motions and we did this analysis and we found out that, okay, we can obtain the PGA at which the boulder started shaking and the PGA at which the boulder actually toppled. This shows one of the analysis like that. For a few analysis, we also found that the boulder would just shake for a while and would come back to its original position, not toppling. However, there were some shortcomings of this model which we used. So finally, we did the finite element model, which was done by Bozdak et al. In 2017. And we developed and we used this model to obtain the ground motions for Mars again. In this, you can see that we are nicely able to capture the multi-orbit waves also, which are observed on these planetary bodies. It incorporates the topography and the 3D variation of material properties as well. That's it. Thank you. So I would like to conclude that the work that I did for the seismic source, the extreme value theory certainly provides very good estimates for the regions of strong motion generation. The work that I did for reduced micropolar medium can we use this theory or explore this theory for explaining some of the other concepts that we observe in seismology? And certainly, the effect of complex topography should be considered when we are simulating the ground motions. Thank you.